All right, everybody, it's me again. Today is Wednesday. I'm Jed Sundwall. I'm going to talk about Source Cooperative really quickly. I do want to, first of all, I just really enjoyed this morning's presentations, and I want to, I mean, a lot of what I'm going to talk about here is going to riff on like what Ryan was talking about in terms of like the basically like the evolution of how we work with data on the internet. And so Source Cooperative is the way I've described it to a lot of people is that my background is I created the open data program at AWS, where the long story short there is that I showed up at AWS and had very few resources available to me in terms of like engineering and things like that. But I did have effectively unlimited S3. I figured out, oh, I can just give away as much S3 as I want, basically. If we're recording this, but so maybe I shouldn't say too much of this stuff out loud. But like I figured out we had a lot of S3 we could give out. What can we do with object storage? Like how far can we push things? And then also, how would we make data available in such a way that like anybody could, the term I landed on was like approach the bucket, you know? And like if you come to an S3 bucket, you find yourself with a large data store, would you be able to like navigate it at all and find your way around? And that led to us, putting Landsat on AWS, which the process of that, we sort of accidentally created what's now called the COG. That led to Stack. And I first encountered Ryan through the Medium posts about data portals, I think, that, where I felt like it was very clear that a lot of smart people were recognizing that there's a new way of working with data. So what we're doing with Source Cooperative is basically trying to create a cloud agnostic version of the open data program, of just like how, if you're just going to make buckets available to people, how would you do it? And also riffing on what Ryan was talking about in terms of like the different like modes of sharing data, whether it's object storage or file storage, or like databases and things like that. Source Cooperative is explicitly just object storage. It's slow. It's intended for what I would call fully baked data products that are done to be published, which is not everything, right? So like it's not intended to be sort of the end all be all data platform. It's really a place where fully baked data products can go and be published. I'm not going to belabor our thinking on cloud native because a lot of this has been covered. But I want to shout out, and Kyle's in the room as well, I want to shout out Development Seed for creating the guide to cloud native formats. If any of you, I mean, I can tell based on people in the room, but if anyone's like curious about like the whole cloud native scene, as I call it, we're a scene now, go to guide.cloudnativegeo.org, and that's probably the best place to look at that stuff. And all that content was created by the team at Development Seed. Kyle had a heavy hand in that. So I want to focus instead on like our emphasis on object storage and why we think it's useful. So there's this concept of pace layering. This came from Stuart Brand. At least that's where I got it from. Where the idea that like the life that we live, our existence as humans, the way we experience the world is built on top of like all these layers of things that are constantly changing. So everything's always changing. We should accept that. But the rate at which certain things change is different, right? And so there's a sort of like fundamental substrate of what we could call nature that changes somewhat slowly. Culture moves more quickly on top of that. Governance is informed by culture. And you can already see right there at that low level of how like all these layers, they influence one another. There's a lot of interplay among these different layers. There's infrastructure, commerce, and then fashion is just kind of the zany thing that's able to happen on top of all of that. I think this is a really fun way to think about the data infrastructures that we're building and how we interact with data and technology. So the way we see the world is that, yes, once again, nature undergirds everything, and on top of nature is the internet protocol. So like a very fundamental internet protocol. On top of that is HTTP, so that's hypertext transfer protocol, in case you'd forgot that. I would argue that on top of that comes standards or patterns and best practices for file formats and metadata that can be shared over HTTP. And on top of that, and so again, there's a lot of interplays here. You have sensors. We're going to be deploying. We're always creating new instrumentation and new ways of producing data about the world. those actually, I think, are based on the way that we produce the data from sensors is heavily informed by the standards below them. So you're not going to produce a new sensor that's going to produce, well, I mean, some people are going to try to create sensors that will produce an entirely new kind of like file type or file format. But generally, they're like, no, we're going to put out netcdf data or CSVs or something like that, JSON files. And then what I want to have happen is to have interfaces, have many more interfaces and ways to interpret data, akin to fashion, where it's getting cheaper and cheaper all the time to produce wild interfaces that interact with data. Like that's the vision that we have for the world. And so what we do, and I've already talked about our work in the beginning, but we see that Source Cooperative is basically a way of encouraging people to share data over HTTP. And then our work with the Cloud Native Geospatial Foundation is to figure out a lot of the stuff that Ryan and Brianna talked about, which is like, how do we work on top of commoditized object storage? There's the fact that it's now possible to share petabytes of data over the web. How do we actually govern and motivate like the continual development of patterns and best practices to, from a community standpoint, to do that well? And I think we can all agree that this governance issues here just have not been solved. There's been attempts at doing this by like having groups like HDF Group manage this stuff, or having OGC figure out how to do these things. None of the solutions are perfect so far. And so these areas of governance are really where we're experimenting a lot with the Cloud Native Geospatial Foundation. Now, so let me just, like I said, oh wait, I'm out of time. So I'm just going to leave it at that. I was going to talk about Source as kind of like the finder for the internet, but I think this is enough. We're going to have 2 days together, so I'll leave it at that and hand it off to Alden.
Hi everyone. Yeah, I'm going to say again, I'm just excited to be here and get to meet you all. Before I get into this, a little preface that I'm a fairly noob at this whole community, so I might say some things and you'll be like, that already exists, someone already did that. And that's part of why I'm here, to tell me about these things. I definitely don't, I know there's a lot of work that has been done in the past by some really smart people on the things I'm about to talk about, and I don't want to discount any of that. Okay, so over the last about 8 years, I have been co-founder and CTO of this company called Upstream Tech. And a big thing we do is make machine learning based river flow forecasts. And those forecasts rely very heavily on weather data. And so I spend a lot of time getting weather and then also satellite data somehow from the various places it is on the internet into our models. And that process has, over the years, maybe come to the conclusion that getting weather data is a pain. And as I've been thinking about that more, it feels like that is really holding back like our ability as humanity to make tools that are going to allow us to adapt to climate change, because we're going to need to get a lot smarter and stop being surprised every time an extreme weather event happens. But right now it feels like the hundreds of thousands of people out in the world who can write computer programs are not being able to write them to solve their climate impacted problems that they are having because of how challenging it is to go get the weather data. Besides that, like so much of the tooling is already there and works really, really good. But at least for me, by pain, I mean, every time I want to go to get to a new weather data source, I probably have to go write some more bespoke code, more than I would like. And then even once I do that, just like, and optimize that code quite a bit, just because of how the data is stored and where it is stored, it often takes what I would say is too long to get it. Days and weeks when I think it should be like minutes and seconds. So I wanted to make basically I was asked the question, could it be a little bit better? So I decided to start with the Meso-West Zarr archive that's on S3. So this is it's Zarr, so it's already cloud optimized. It's live updated. They updated very frequently. Each time a new forecast from the HER model comes out. Sorry, HER is a high resolution weather model run by NOAA that covers the United States, continental United States. And to my mind, it's like the only live updating cloud optimized archive of what I would consider a top tier weather model that exists. I don't know of another one that actually is in a Zarr that is kept up to date, and it's a forecast that like I would put into a model that I want to use. So I feel like it's a fairly strong baseline there, and I wanted to just go through kind of and see if it could be improved on. So the experiment was basically try to do a little bit better choices on, or better, see if I could optimize the chunking of it, the compression of it, where it was hosted, and then reading, particularly to maintain the already, I would say, good enough latency in terms of reading it. That's basically because the chunking that they decided on is very small. So, and it's on S3, so you can get like a tiny chunk pretty fast from pretty much anywhere. So that to me is like good enough. And the challenges are really with this data set, the throughput, like how long it takes to read a lot of the data set. That's what I mean by throughput. By latency, I just mean like round trip time if I want to get a small little bit of the data. So for this tiny little prototype, I took 1 month of data from HER across the entire continental US domain. It's at a 3 kilometer pixel grid resolution. I took just the air temperature data at the surface of the Earth, and I just took the like analysis. So it's as if it's like the observation. So it doesn't have a forecast lead time that's like stepping out into the future. It's just like, could you play me back this model's best estimate of the temperature in June 2023. And then for each of these things, I picked, just based on my past experience, some like probably decent choices for them. So for chunking, I was thinking, if you were to redo this with weather data at a bigger scale, you don't necessarily know whether people want the churro or the pancake. So I would pick something kind of in between and go with scone. This is a V2 Zarr, so I had to kind of trade off chunk sizes, both to maintain the latency side of things, but also try to improve the throughput. So I went with about a 10 megabyte per chunk once it was compressed. I know you could get quite a bit higher throughput if you made these bigger, or probably you could get the higher throughput if you made these bigger, but I didn't want to mess up the latency of getting just one little bit of the data. In my experience using Z standard with level 9, just like turn it up to 11, even though it takes a bunch of CPU cycles to compress, got out pretty darn good compression in it's lossless, although the archive, this HERZAR archive, they are storing the data in 16-bit floats. So there is some loss going on from the source data there. And then in terms of hosting, I put it on a cloud object store and then put a CDN in front of it. I happen to use Cloudflare for this, but I have no shell for Cloudflare. I just wanted to like have a CDN and see what that would do to it. And then for reading the data, I read it with like current released version of Xarray in Python. And then also because I wanted to learn Rust, I tried hacking up a little thing myself in Rust. It wasn't actually using a Python library. It wasn't using a Rust implementation. It was literally just like make an HTTP request, compile the BLASK library to decompress it, and like run through some numbers in there. It's disgusting code. I was just wanted to learn how to do Rust, try Rust. So okay, results in terms of time. So the latency test basically like passed my okay threshold, which is you could still get any chunk in less than a second. And then in terms of throughput, what I was calculating is just like take the average value across all the temperature over the whole month across all the space domain. And when I was doing this with the MesoWest archive and Xarray, along with like a little bit of optimization on the opening to like parallelize the getting a little bit too far into the details, in this MesoWest archive, they actually store a separate Zarr for every single issuance of the forecast. So you got to open all of those with like an open MF data set or like just in parallel and then concatenate them in order to get the time dimension there. But I did a thread pool to do that side of things like that. So that wasn't like, really making, I think that's a fairly fair comparison there. And then, so I ran that on some, and I ran all these tests, these 4 tests basically on a 16 core, like, pretty nice instance on GCP, Google Compute Engine, but it was a spot instance. Like it costs like $52 a month if you were to rent this instance for the whole month. So it's not like breaking the bank. That's the 16 core one at the top there. And the 2 shared core one is like a teensy little cheap machine. It costs you $2 a month as a spot instance. Anyways, it's a lot faster, like quite a bit faster. Using the prototype plus X-ray here is the Zarr that I reconstructed and rechunked and all that, and is able to analyze this in about 3.5 seconds. To zoom in, just because you're just on the prototype version of things here, you can definitely see like the 16 core machine is faster. That's both because like they give more internet like bandwidth to those bigger machines, and also it's got some more CPU. But I think my main takeaway is like, you don't need to rewrite everything in Rust. The existing open source tools work just fast enough in this case. Really, it's like the redoing the chunking and compression and probably the CDN that are giving the biggest benefits here. Should we do this for all the weather Zarrs everywhere? Or all the weather data sets? It's exciting to me to think about like what people would be able to build if all of the best weather data sets were reformatted like this. I know that's it's easy to say that, and that would be like a very large challenge to do. So I'm curious, I know people have tried this before. Like if I was to go try to do this, why would I fail? Tell me about those reasons today. Metadata specs. I think it'd be really awesome to be able to run something like this line of code where you just like merge together multiple data sets. And I think that probably intersects with what people have already been talking about here. So I'd love to talk about that more if anybody's interested. And then in terms of like tools and libraries to do this, I know about PangeoForge. Are there other like things I should know about? Anyways, I'm excited talking about this to think about what it could be. You'll notice like Upstream Tech's logo is not on this presentation because it's not something that Upstream Tech is going to go do by itself. Like we're a forecasting company, but maybe this is something I still work on outside of that. So anyways, thank you.
Okay, my name's Christine again. So I work at the GESDISC, which is one of NASA's Earth Science archives. And so I'm going to be talking about a tool we built on top of Zarr, because I think that was the original prompt, was something about what have you done with Zarr? So this is what we did with Zarr. This work was not just done by me. Brianna is here as well, but there's like a whole team at NASA who were involved in doing this. So we are, I can never remember what we stand for, but we're the GESDISC. We archive and curate science data. So NASA has a whole fleet of Earth science satellites. In fact, crossing fingers, PACE is launching tonight, hopefully, if the weather is agreeable. It was delayed 2 nights, but hopefully tonight's the night. My husband worked on it, so we're very excited. And then beyond the basic data, we also create services that hopefully make that data easier to use. The complexity of the data is something that we do appreciate and understand, and we do try to make that better incrementally, as time goes by. It used to be it was all custom data formats. At least now, like, you're going to get some kind of a standard data format, so SCORE. So the specific task we were given was to migrate this time series service. So we have a hydrology service on premises. It's called Hydrology Data Rods. Churros is a much nicer, catchier term for this than data rods, I have to say. But it sought to address that chunking problem that we were talking about, and made everybody hungry. So the data coming to NASA is usually pancakes. I'm going to use that from now on. It's an excellent term. It's usually pancakes which sort of makes sense because we have these instruments that make an observation, that observation comes down to the ground, it gets processed, blah, 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 it gets archived. And then there's new observations, it comes down to the ground, et cetera. And since we tend to make those observations at a particular point in time, we end up with this kind of latitude and longitude pancake for a particular time step. But if you want to get these long time series, that data is terrible because you have to open, you know, potentially millions of files just to get like 1 or 2 data points out of each one. So this project actually happened years ago, and the data was rechunked in that CDF format on premises, one server, et cetera. So there were some issues with the way that worked. Having one server means that, you know, it doesn't scale well. So we were tasked with moving this into the cloud. And what we did is we moved it into Zarr stores in S3, chunked as scones, because we wanted to have reasonably fast access along any dimension. We do have plans to include other services, not just time series. So it made sense to not just, you know, throw churros in the cloud. So just as an example, yeah, let's see if I can get this to open. Oh, right. Tell you what, I'm not going to run this on here because I'd have to enter my username and password. Okay, so you'll just have to believe me and or try this for yourself. It's, you know, you do need to have Earth Data login to do it. But Earth Data login is free if you don't already have one. So behind the scenes, the Zarr store is global, 0.1 degree data. It's 23 years, half hourly. So it's a fairly large data set, and we can get these long time series out in seconds. So then what are we in the process of doing? So we use Zarr behind the scenes. The way we currently do it makes it a little tricky to make the data stores public. It was always our plan to make them public, and we are kind of like working on that now. A lot of the complexity is actually around the fact that a lot of our data stores get updated regularly with new data because a lot of the data sets come from satellites that are currently making observations or from models that are continuously running to generate more data. So the first plan is to make Zarr stores public that happen to be from data sets that are complete. So we don't have to worry about that updating issue. But that's where we are. We also, I don't know why I didn't put it on here, but we also submitted a ZEP, actually, we're ZEP 5. And we have open sourced an initial implementation for part of it. Unfortunately, the folks who worked on that were not able to come today, but we are hopeful that this will help kind of with some of those common algorithms that people like to run. So if you like to run averages over contiguous sections of data, then you may have heard of how you can use cumulative sums to speed that up. And so we would have sort of like pre-calculated cumulative sums. And we're working on that. So that's where we are.